question with this? All right. Next one, you have probably another case here. Two skaters of different masses prepare to push off against one another. Which one will gain the larger velocity? So you have the choices. Is it the more massive one will move faster? Is it the less massive one? Or they will have these, the equal and opposite velocities? What's your pick? A, B, or C? B. You sure? Okay, definitely the girl here, the small girl, she's gonna move faster than whatever her mother, because of the mass. Her mass is less, so it's inversely proportional. When the mass is less, the velocity is more, and when the mass is more, the velocity is less. So the answer should be B, the less massive one. All right. We looked also at this example. Is the momentum conserved when shooting a shotgun? What do you think? Is the momentum conserved? So here the shotgun, the bullet, and the rifle, they were together, and they were then after that they separate. So is the momentum conserved? Let's see. The explosion of the power causes the shot to move very rapidly forward, and if the gun is free to move, it will recoil backward with a momentum equal in magnitude to the momentum of the shot. So even though the mass of the shot is small, the momentum is large due to its large velocity. So what he's telling you, the bullet here is very tiny with low mass, so it's going to move with very high velocity, while the rifle here has big mass, so you're going to have kickback, but the velocity of the kickback is not that large. Okay? But the momentum is the same. As you see here, P and P, one of them is positive, the other one is negative. The momentum for the bullet should be equal to the momentum for the rifle. Alright? Remember, large mass, small velocity, small mass, large velocity. Alright, how can you avoid a bruised shoulder? Alright, so how we could do that is by putting the rifle against your shoulder. Don't leave a space. Don't leave any space. If you leave a space, you're going to have a broken shoulder. So you put it against your shoulder. Okay, why against your shoulder? Because also you're going to increase the mass. If you put it against your shoulder, what will happen here, you're going to count the mass of the rifle plus your mass. Your mass plus the mass of the rifle, then you're going to have minimum kickback. You don't feel it, even you don't feel it. So you increase the mass, you decrease the force on you during the shot. Alright? So this is how you avoid it. It said here, if the shotgun is held firmly against your shoulder, it doesn't hurt as much. Alright? Why? Well, I already explained it. You increase the mass. So it's going to be your mass plus the mass of the rifle together. Alright, let's look at elastic and inelastic. You're going to see in case 1, you have the ball is hitting the wall and rebound. So this is perfectly elastic when you see the velocity is going to be equal. Like say velocity final, velocity initial. How about here? This is definitely inelastic, perfectly inelastic, because the velocity initial, you have a number here, while this is going to stuck there. Let's say, and I gave an example on that. That's a mud ball is hitting a wall, and the mud ball is going to stay there, it's not going to move. So that's perfectly inelastic. In fact, well, if you want to look at it this way, maybe this is a simpler way to learn the elastic, inelastic, and partially inelastic. When you see velocity final is equal to velocity initial, learn it as perfectly elastic. When you see velocity final less than the velocity initial, then this is partially inelastic. I think this is the easy way to learn. Velocity final less than velocity initial, then this is partially elastic. Velocity final 0, definitely perfectly inelastic. The example on that, as you see there, but there are many examples. Two cars going against each other. Initial velocity, they hit each other, they strike there, they stay there. Velocity 0. Perfectly inelastic. Okay, because the velocity final is 0. So always when you see velocity final 0, then that's perfectly inelastic. I think that's the easy way to learn. Alright. Any question? Okay. Different kinds of collisions produce different results. So when the objects stick together, or sometimes the object bounce apart. So you have different cases anyway. Let's look at this case. What you have here, a collision with the objects stick together after a collision is called perfectly inelastic. Alright. So let's see here. The example here, football player who stay together after they collide is perfectly inelastic. Stay together but stay the same. Coupling railroad cars. Coupling railroad cars. So let's look at the example. I think there's the numbers here you have to find. You have 4 railroad cars. 4 railroad cars. All with the same masses of 20,000 kilograms. Sit on a track. A fifth car of identical mass approaches them with a velocity of 15 meters per second. So here, this fifth one has a mass of 20,000, is moving with 15 meters per second. The masses here all together, you can add up 20,000, 20,000, 20,000, and 20,000. So that's the total mass of those 4 cars. Alright, what is the initial momentum of the system? Very easy. Is it 2,000? Is it 200,000? 300,000, 600, or 1,200,000? What's your choice? The 4 cars are stationary, right? Did you say stationary? Those cars? The same masses sit on the track. Sit on the track, that means they are stationary, they are not moving. Well, this one, the only one is moving. So what's your answer? A, B, C, D. What is it? How did you find that? What's the equation of the mass? Equation for the momentum. Mass multiplied over velocity, right? Okay, so multiply that, what do you get? 200,000? 300,000, B. Okay. So the answer is 300,000. And because the other ones are stationary, they are not moving. Alright, so that's it. 300,000. Next one. What is the velocity of the 5 coupled cars after the collision? 1, 2, 1, 3, 5, or 10? after the collision, what is the velocity of the 5 coupled cars? What is it? 3. Okay, you got it. 3. Alright, any question on this? And that's how you solve it. I'm going to upload this PowerPoint on the Blackboard so you can see the answers and check your answers. Alright, so that's how you solve it. Next one, is the kinetic energy after the railroad cars collide equal to the original kinetic energy of car 5? Yes, no, or it depends? What's your answer? Kinetic energy after the railroad cars collide. Is it equal to the original kinetic energy of car 5? What's your pick? No? You got it? No. No. Why? Well, because it is substantially less than the kinetic energy because of some of the energy is lost due to sound, due to friction. The fifth car with the other cars, and that's why. You're not going to have equal kinetic energy. Definitely not. Alright. And if you want to verify it, if you want to prove it, you need to find the kinetic energy of the first one. And you have the equation, 1/2 the mass times velocity squared, 1/2 times 20,000 times 15 squared, and you get that number. And then the kinetic energy final, which is this, also 1/2, and that 100,000, the mass of those 4 cars, fifth car, 5 cars here, and multiplied by the final velocity squared. So you're going to have 450, and 450 kilojoule is not equal to 2,250 kilojoules. This is how you prove it. But common sense, it's not equal. What is that? That's 800, right? And this is after the collision is going to be together. They collide. So you're going to count this as 200, so 100,000 after the collision. So those are the cars, and stationary before, but this is moving with a velocity. Hit them, and they moved a little bit. They moved a little bit with velocity of 3 meters per second, and they stopped. So now together, 5 of them after the collision. All right. Any question on this? Okay, Bin Salim, I'm going to upload this. Don't worry about it. Okay. Next one. We know this. Energy is not conserved. That means perfectly inelastic, or partially inelastic, or elastic perfectly.